we present ImViD, Immersive Volumetric videos for enhanced VR engagement. Recent developments on 3D video formats have shown success. Most notable ones such as Google's 6 Degrees of Freedom immersive light field, as well as Apple's new spatial video with stereo audio. While they show great progress, they are yet to reach full immersion. Achieving complete user immersion is a goal pursued by many researchers in the VR realm, leading us to the concept of immersive volumetric video. But what defines an immersive volumetric video? We believe that immersive media should possess the following characteristics. First, full 360 degrees viewable scene. Second, high-quality 6:2 interaction, which current volumetric video can achieve. Third, multimodal experience with 3D stereo sound. Fourth, high frame rate and long-duration content. We address media formats that meet all these criteria as immersive volumetric video. Our contributions are as follows. We propose ImViD, the first immersive volumetric dataset to our knowledge, featuring multi-views, multimodality, 360 degrees viewable space, shot in long duration at 60 FPS. Second, benchmarks of ImViD on latest 4D reconstruction methods. Lastly, a pipeline for reconstructing light and sound fields. Let me first introduce our data acquisition method. Handheld monocular camera is easy to move, providing limited perspectives from various locations, while fixed camera arrays offers dense perspectives yet with a limited range. We aim to combine the advantages of both for efficiently capturing data for immersive scenes, a feature not found on existing datasets. Thus, we designed a mobile capture rig employing a two-step acquisition strategy, enabling both fixed and moving collection of multi-view video and audio data, along with a 360-degree image acquisition of static environments. We captured data from a total of 7 indoor and outdoor scenes. A detailed analysis of the dataset is presented below. Please refer to our paper for details. Examples of acquired raw video footages are demonstrated. They feature 5K resolution at 60 FPS with synchronized audio. The example in display right now is captured at a fixed location. The one in display right now is captured in a moving strategy, where we simulate the potential movements of real-world VR users.
There's a very interesting geographical feature in West Marin. Between the main part of Marin County and West Marin, or rather this area called Point Reyes, is a place where two different zones, subduction zones.
To validate the effectiveness of ImViD dataset, we provide benchmarks for dynamic novel view synthesis. We conduct thorough experiments to analyze the strengths and weaknesses of three 3DGS-based dynamic scene reconstruction paradigms: 4DGS, 4D-Rotor, Spacetime GS. This allows us to compare and further develop one baseline model for improvement, which will be integrated into our immersive volumetric video pipeline. Shown here are the results. STG outperforms all baselines in most scenes, whether in train view or test view, delivering slightly better results, the highest rendering speed, and a moderate model size. However, the algorithm's performance is still affected by its segmented training strategy, as well as by color inconsistencies between adjacent views in real scenes, resulting in flickering and floaters in long-duration videos. Thus, we introduce STG++, a refined version of vanilla STG with an integrated affine color transformation module. Here shows more reconstruction results of STG++. Lastly, we propose the complete pipeline, from data capture to light and sound field reconstruction, and to immersive volumetric video. We reached millisecond-level alignment between sequences based on precise video time codes, and fully utilized the relative positional relationships and prior intrinsic parameters when calibrating the cameras. In sound field reconstruction period, taking the recording microphone as the origin of the coordinate system, we denote the coordinates of the sound source as XST and YST. The user wearing the VR device as XLT and YLT, and the angle of deviation from the y-axis in the counterclockwise direction as theta LT, where t is the time index. We first do sound direction mapping. We calculate the direction of the sound source relative to the user's ears. This direction is denoted as theta ST, and it is calculated as follows. Next, we do sound distance mapping. We calculate the scaling of the sound source when it reaches the user's ears, relative to the original recording. We denote this scaling parameter as lambda t, which is calculated as follows. Finally, we do sound oralization. We convert the original recording into spatial audio based on theta st and lambda t. This process can be described through the following equations, where A left and A right are the audio from the left and right ears, respectively. F left and F right are head-related transfer functions. We utilize theta st to retrieve F left and F right from a HRTF dataset. FL denotes the room impulse response at the user's location, and AO is the sound emitted from the speaker. In order to model FL and AO, we make the following assumption. FL change between different location only depending on the parameter lambda t. Using this assumption, FL times AO can be simplified as lambda t times A, where A is the recording microphone signal. Using these equations, we can finally convert the recording sound into the spatial sound. We then integrate the reconstructed light and sound field to achieve an immersive 6DoF VR experience with rendering speed at 60 fps on a single 3090 GPU. Here we visualize the interaction trajectory and corresponding visual and auditory results. Note that the multimodal feedback changes accordingly to the positions and orientations. Please wear headphone for fully immersive experience. To summarize, in this work, we define immersive volumetric video for enhanced VR engagement. We have achieved impressive results in building dataset, benchmark, light, and sound field reconstruction pipeline, but there are still issues need to be solved. Robust calibration and reconstruction methods for data collected from our moving rig. Improvements for training strategies on long-duration dynamic scenes. Stereo sound fields reconstruction with multiple sound sources. Thank you for watching and listening.